Hey everyone, welcome back. It's week 11. I just came back from my trip and I'm back continuing studying. So this week I completed section 3.3, which is all about conjugate functions. So today I want to build up some geometric intuition first, and then let's look at some examples that are directly relevant to your machine learning. So let's get into it.
Alright, so let's start with the picture. Imagine you have some function f of x here. So it could be any shape, but let's say in our example it looks like this. Now what we do is pick some slope y. And so, for example, if y was 5, then the function 5 of x would look something like this. But we just pick some arbitrary slope y. So yx is a line like this. Now at every point x, there's a vertical gap between the line here and the function. So the conjugate function written f star of y is just asking what is the maximum possible gap over all of x, how wide can this gap be? So we have this conjugate function f star of y is the supremum of the gap function, which is the difference between y of x minus f of x for some x. And so we try to find the x, which is the supremum of the gap function. So that's pretty much it. That's the entire definition. So we're just to reiterate, we're asking for a line of slope y, what's the largest vertical gap it can have with f? And the answer as a function of y is f star of y. So here's a different geometric insight. So let's say in our case that f is differentiable. Then the maximum gap between the function f and the line yx occurs exactly when the line is tangent to the curve. So in this case, you can see the function here is at this point is tangent to the curve here. Sorry, to the line. That is when f prime of x equals y. So f star is secretly encoding information about tangent lines of f. To see why this is true, you take the gap function. Let's just define g of x is y of x minus f of x. Take the derivative, set that equal to 0, and you see that f prime of x is equal to y. So that's when the gap function is maximized. So this is actually important later. It transforms x from a function of position x into a function of slope y. So you're kind of switching coordinate systems in a sense. So instead of describing the curve by its height at each point, you're describing it by the intercepts of its tangent lines. There's also one immediate consequence of this definition that I want to mention before I do any examples, because I think it's important, but I think it's also remarkable. F star is always convex, no matter what f is. So f can be super messy, but f star of that function is always going to be convex. Oh, and then before explaining why, just a little technicality. The conjugate is defined in higher dimensional space. So instead of y times x, we have y transpose x. So these these y's and x are in R-of-n space. Okay. All right. So back to what I was saying. Why is it that the conjugate f star is always convex? Well, it's because for each fixed x, the expression y transpose x minus f of x is just an affine function of y. So it's a hyperplane in y space. And f star is the pointwise maximum over all of those hyperplanes. And of course, the pointwise max of affine functions is always convex. So we saw this before. Alright, so let's do our first example. For this example, we take the quadratic f of x. So this is a 1/2 x transpose q times x where Q is a symmetric positive semi-definite. So what we want to do is we want to find f star of y, which means we want to maximize y transpose x minus 1/2 x transpose qx over x. So since f is differentiable and convex, there's a unique maximum. So we can find it by setting the gradient to 0. So the point x which maximizes this expression is when x star is equal to the inverse q times y. So now we simply plug in these results back into the original equation. So we plug in, instead of x, we plug in x star, which is the expression here, simplify a little bit, and we get this following expression. And there it is. The conjugate of the quadratic with matrix Q is the quadratic with matrix Q inverse. So that's a really beautiful result, right? The curvature kind of flips. If Q made F very curved, that is, like sharp and narrow, then Q inverse is flatter and F star is wider, and vice versa. And the conjugate and the original function are inversely related in their curvature. Also notice that the domain of f star is all over R of n, and this is because the supremum is always finite. Okay, great. So let's do the exponential now. So that's when f of x equals e to the x. So the domain is all of real numbers, right? Like before, of course, f is differentiable, so we just differentiate, set it to 0, and find the x which maximizes the gap function. Okay, and it turns out, do the calculus, and you get x star equals log of y. And like before, we could just plug that in. Okay, we plug that into the gap equation, and we get y log y minus y. But notice that the domain of this conjugate function is not all real numbers, right? Log can't have an input that's negative, so it must be non-negative numbers. Lastly, let's look at the log-sum exponent function. So we see this in everywhere in machine learning. And as before, we want to maximize y transpose x minus fx, which is the gap function. And so taking the gradient and setting it equal to 0 gives us this expression here. So look at this expression on the right side here. It's the softmax of x. This means the automality condition is y equals softmax of x. So for this to be a solution, y has to look like a probability vector, strictly positive entries, summing to 1. So that's the domain of f star. And when we plug in the optimal x back into the expression and then simplify, so we get the final expression that f star y is the negative entropy of y, right? So the conjugate of a log-sum exponent is a negative entropy on the simplex. And by the conjugate of the conjugate theorem, which I didn't mention, but you can probably see that the conjugate of conjugate is the function back. Negative entropy of the simplex conjugates back to the log-sum exponent. So these two functions are kind of dual to each other. So this is like why entropy, regularization, and other things, and the softmax function all play so nicely together in machine learning. Okay, so before I wrap up, I want to mention Fenchel's inequality because I was told that Fenchel's inequality shows up everywhere, apparently. So here it is. So first, we have to derive it. So, from the definition, we have this, which of course is greater than or equal to any other gap function. To be more clear, I mean that the supremum, takes the biggest one. So if you take any other one, then it's going to be smaller, right? Okay. And then what you do is you simply rearrange this expression, and you have, f of x plus the conjugate f star of y is greater than or equal to y transpose x for all x and y. So this is called the Fenchel's inequality. So if you know real analysis, if you take a real analysis, it's kind of like a generalization of Young's inequality. It tells you that the sum of a function and its conjugate provides an upper bound on an inner product, which becomes an equality at exactly the optimal point. So this equality condition is what drives a lot of duality theory, at least I've been told. Lastly, one more thing, I mentioned earlier, but I just want to make it clear, the conjugate of the conjugate is f, provided that f is convex and closed. So you get back the original function. So geometrically, this kind of makes sense. The conjugate was a re-encoding f through its tangent lines. Taking the conjugate again should decode it back. So the transformation is an involution of the space of closed convex function. So this is why sometimes people say conjugation is a duality. You get a perfect two-way street between f and f star. The log-sum exponent and negative entropy example we just saw is an instance or example of that.
So hopefully that was pretty cool, seeing how the geometry ties in the conjugate. I noticed this sort of pattern happening over and over and again. You take some arbitrary mathematical object, in this case, the conjugate, and it, just so happens that, this mathematical object has deep implications for optimization and machine learning. And, it shows up everywhere if you know where to look. So this is why I like studying this stuff. Yeah, so with that said, I'll see you next week.